Good morning, students. I am Arokiamary, Assistant Professor, PG and Research Department of Mathematics, St. Joseph's College of Arts and Science, Autonomous, Cuddalore. I am going to explain Laurent series, which is part of complex analysis for PG students. Statement of Laurent series. Let f of z be analytic in the annular region R1 less than modulus of z minus a less than R2, then f of z can be expressed as f of z equal to summation n varies from minus infinity to plus infinity an into z minus z naught power n, where an equal to 1 by 2 pi I integral over c f of zeta by zeta minus a power n plus 1. For Taylor's series, the region is simply connected. That is, we had modulus of z minus z naught less than r. Whereas for Laurent series, we have the annular region, that is doubly connected region, R1 less than modulus of z minus a less than R2. So, we split f of z as f1 of z plus f2 of z, where f1 of z contains the positive powers of z minus z naught and f2 of z contains the negative powers of z minus z naught. Given f of z is analytic in the annular region R1 less than modulus of z minus a less than R2. Now let us consider the second inequality, that is second part of the inequality, modulus of z minus a less than R2. That is, we consider the region modulus of z minus a less than R2. Now this is as in the statement of Taylor's. So let C be the circle, modulus of zeta minus a equal to R, so that capital R1 less than R less than R2. That is, this circle lies within the annular region. Now f of z is analytic in the region, and so it has Taylor's expansion about A. That is, we can write f1 of z as summation n varies from 0 to infinity an into z minus a power n, where an is 1 by 2 pi I integral over c f of zeta by zeta minus a power n plus 1 d zeta. That is, as in Taylor's series, we can express f1 of z. That is, we have derived the positive side, positive powers of z minus a. Now to find f2, we consider the transformation, that is, we put z minus a as 1 by z dash and zeta minus a as 1 by zeta dash. So, cross multiplying, we can write zeta dash equal to 1 by zeta minus a. Now you know zeta minus a is r e power I theta, because modulus of zeta minus a is r. It is 1 by r e power I theta, or we can write it as e power minus I theta divided by r. If we consider C naught as the circle, modulus of zeta dash is 1 by r dash, then C naught is negatively oriented. Now we can write f of zeta as f of a plus 1 by zeta dash. Since zeta is a plus 1 by zeta dash, differentiating we get d zeta as minus 1 by zeta dash square into d zeta dash. And zeta minus z will take the form minus a minus 1 by z dash, which is minus z. Then zeta is a plus 1 by zeta dash. A gets cancelled, and by taking LCM we'll get z dash minus zeta dash divided by z dash into zeta dash. Now f of zeta d zeta divided by zeta minus z. That is f of zeta is a plus 1 by zeta dash. So f of zeta becomes f of a plus 1 by zeta dash. And 1 by zeta minus z. From the above we write z dash zeta dash divided by z dash minus zeta dash. And instead of d zeta we write minus 1 by zeta dash square into d zeta dash. So we get f of zeta d zeta by zeta minus z as f of a plus 1 by zeta dash divided by z dash minus zeta dash into zeta dash is the dash into minus 1 by zeta dash square into d zeta dash. By Cauchy's integral formula, we can write f2 of z as 1 by 2 pi I integral over c f of zeta by zeta minus z d zeta. Now we substitute what we have calculated. That is, instead of f of zeta by zeta minus z, we write in z dash and zeta dash. Therefore, this becomes 1 by 2 pi I integral over c naught z dash by zeta dash f of a plus 1 by zeta dash divided by z dash minus zeta dash into d zeta dash. Now we consider this as the summation n equal to 1 to infinity bn into z dash power n, where bn is 1 by 2 pi I integral over c naught f of a plus 1 by zeta dash divided by zeta dash power n plus 1 d zeta dash. That is 1 by 2 pi I integral over c naught f. Now we convert to zeta. F of zeta by zeta minus a power minus n minus 1 d zeta by zeta minus a square. That is, this becomes 1 by 2 pi I f of zeta by zeta minus a power minus n plus 1 d zeta. This is same as an with a negative sign. For an we had 1 by 2 pi I integral over c f of zeta by zeta minus a power n plus 1 d zeta. Instead of n, here we have minus n. So bn is nothing but a suffix minus n. That is f2 of z equal to summation n equal to 1 to infinity a minus n z minus a power minus n. That is, now you substitute f1 and f2 in f. So we get f of z is f1 of z plus f2 of z, where f1 of z is summation n varies from 0 to infinity an into z minus a power n, plus f2 is summation n varies from 1 to infinity a minus n z minus a power minus n. So combining these two, we can write a summation n varies from minus infinity to plus infinity an into z minus a power n, where an is 1 by 2 pi I integral over c f of zeta by zeta minus a power n plus 1 d zeta. Here zeta is arbitrary, provided r1 less than small r less than capital R2. Hence the proof. Hope you have understood. Let us have a glance.